So this is 2 years ago. This is getting on the Garden State Parkway, which is near the NVIDIA office in Homedale, New Jersey. And First Fuller was with the safety driver's seat. Jan LeCun is taking a picture with his cell phone. And I was in the back seat holding my breath. So we go through the toll booth, and it wasn't trained on that. So that was pretty amazing. This was trained on just driving in that general area. So I want to talk about how this was done and where we're going from there. So the current status is the mean autonomous distance for just driving with the front-facing camera. It's about 100 kilometers on highways. It's good enough that the passengers can doze off, which means it's extremely dangerous because it's hard to pay attention. But it's not good enough that you can go to sleep and wake up alive. We need to get, I guess, about 4 orders of magnitude better before this stuff is really product worthy. So there's a lot of work to be done. One thing I want to emphasize that the work I'm describing here is only a small part of the work on autonomous driving done at NVIDIA. NVIDIA, of course, is making GPU hardware, which you all know about, but there's also strong efforts in mapping, localization, route planning, controls, etc. We're only looking here at lane following, and what we're doing here is also an adjunct to more traditional approaches to lane following. So the traditional approach is that called LaneNet. Camera goes to an algorithm called LaneNet, which is basically a convolutional net that finds the lane markings. It does the path estimation and steering control. And what's happening at NVIDIA in New Jersey is there's a system called PilotNet, which works in parallel with LaneNet and the path estimation. And then one looks at which method seems to have more confidence, then you decide where to go to the controller. So the hope is, still to be proven, that with diverse systems with different strengths and weaknesses, you can get to the required performance that you need. And the very best case, which this is, of course is not, that the error rate for LaneNet, error rate for the whole system will be the product of the two error rates. So if both good, the errors are uncorrelated, you'll be in great shape. Never going to be that good, but you're going to get a big gain by having the diversity. So for the remainder of the talk, I want to discuss how we got to PilotNet. And that's really a long journey in neural nets. And for me, the journey started at Bell Labs in Homedale, New Jersey, which is where I've lived for nearly 40 years now. This is the building that we were in and are in again. The Bell Labs shut down that building over a decade ago, and it's been rented out in parcels. And NVIDIA has rented exactly the same aisle in that building where I had my machine learning group. So the landlord wants to make a little museum there for Jan LeCun, who had an office in that aisle. So we had about 6,000 people in Homedale. There were about 300 researchers that were focused here on a few floors. There were about 30 people in machine learning. What's interesting about the site from a autonomous driving perspective is that it has these ring roads here that go around the building with lots and lots of turns. These are all private roads. And also in the back here, there's some roads that are overgrown over here, as well as the surface area, which we have access to. Plus, when we started, the parking lots are empty. So we had a place to test off the public roads. So we could be certain that what we're doing was not going to hurt anybody. We might run over some geese, we never actually did. And then when we get really confident, we can go out, onto the main roads. There's one over here, one over here. And this is the Garden State Parkway over here, which is a limited access high-speed highway. There's a lot of diversity right in that facility. You don't have to go far to test. And testing is the key. Testing is done continuously. So going back a bit in time, the system that we use is really the same architecture that Jan LeCun and our group put together for doing character recognition, something called LaNet. And it basically does learned feature extraction using convolutional kernels. And this would really combine the architecture of Fukushima's neocognitron from the early 80s with gradient descent learning of the weights. The stuff worked. We weren't really sure why it worked as well as it did, but we had Vladimir Batnik in the group And he really gave us a much more systematic understanding of how to optimize these systems and how to make them work. And there were basically two key ideas from Vladimir, which we still make sure we use today. One is choosing the right structure. We call it structural risk minimization. And that's bringing prior knowledge into the learning machine. In our case, the prior knowledge that we're dealing with a two-dimensional image, so 2D convolutions make a lot of sense. And the other is capacity control. It's matching the learning machine complexity to the available data. To do that, we constantly examine the learning curves. I'm not talking about the learning curve of the error as a function of epoch, but rather the learning curve as a function of the number of examples. And that's extremely illustrative of where the system stands. So I wanted to talk for a minute about the usual approach for self-driving cars. And this is what I saw when I was a program manager at DARPA over 15 years ago. This is how people did autonomous vehicles then. Most folks still do something rather similar today. You have sensors, you do some kind of feature extraction, object recognition. This block is now often combined using convolutional nets. But with the object recognition, you generate a cost map, and you also can use detailed maps with the object recognition to do localization. Together, these two do path planning, and then you do actuation. So this is proven method. It works reasonably well, but that's not the approach that we took with PilotNet. So here we're basically going from the camera, the mission is steering actuation. Now we go and just propose the actual driving path, and the car drives that path. So we learn by observing the human. There's minimal use of handcrafted rules, minimal use of hand labeling, and there's no maps. And I think also a key feature here is that we don't divide the task into subtasks where we have an arbitrary boundary. It's basically a smooth process all the way through, and this seems to be important. The progenitor of this was work done as a pilot for me when I was a program manager at DARPA. This was done by Chris Muller and Jan LeCun. And they were driving this little radio-controlled car through somebody's backyard that was filled with junk. And somebody had spent many hours driving this car that was using training data, and then it drove as well as this. If you look at the image, you'll see this kind of blurry in the middle. That's because the lens was scratched from lots of crashes during the training. This work was based on work done by Dean Parmelo at CMU in 1990 with low resolution using the fully connected net. This project was called DAVE, DARPA Autonomous Vehicle Experimental. That was 2003. High resolution images and convolutional nets. And this the 6-month project. With that, we got about $20 million from DARPA to start new programs, which are surprisingly went back to more traditional methods. But anyway, this is how the system is trained. That for PilotNet, we record the steering wheel angle of the car, or we record the direction the car is going using IMU. That gives us a desired steering command. There's an input from a camera, goes convolutional net, and that puts out a computer steering command. You look at the difference between what's desired and what comes out. You run a gradient descent, change the weights to the CNN, and you run it through, and you get a self-driving vehicle. So this is the initial architecture that was used. About 30 million connections. This has evolved since this was done. And it works, of course, gotten larger as we've gotten more data. I wanted to show you a quick video of what this looks like. Ursula and I went out on a Saturday morning and took the car on the Garden State Parkway, put it in the middle lane, and said, okay, drive. And we let it go wherever it wanted. We didn't change lanes, but the parkway kept splitting and going off in crazy places. And it wound up going into Woodbridge, New Jersey, into a shopping mall. I edited the video down because I wanted to show the places where it was where the lane markings were messed up or missing. But there was no driver intervention here at all. This was done in the fall of last year. This was about a 20-minute drive. So here the paint was spilled when they painted the lines. Here there's no lane markings on the right side. One thing I think it's important to mention is that when we were in the car, both Ursula and I had our eyes glued on the road. We weren't looking down, not paying attention, because our lives are on the line, and so is everybody else. This is serious stuff. When you saw there's a little green thing, we call that the noodle. That's evolved over time. Initially, it was showing 10 versions of noodle, each generated in 30 milliseconds, and then we would average the noodles and figure out where to go. Now we just generate one noodle, we pick a point in that as a target. So the question everybody asked, of course, what is this system looking at? So we did some work to look for what the network pays attention to. And these are some examples. The highlighted green areas are which are the ones that are most salient for the navigation. You see here the dash lines that are direction travel, the lower parts of the car show up. The crosswalk doesn't. Here we have, there are no lines in the street, so the cars, bottom of the cars are important. This is just grass road on the Bell Works, the Bell Labs ring road, and just picks up the edge between the road and the grass. So people have asked me what happens if there's an atypical vehicle class that you've never seen before. So we were driving out through the exit of Bell Works, that's the name of the site now, and this is what the scene looked like. This is the display we have inside the vehicle, and the region of interest that we look at is here on this green box. And lo and behold, there was this front loader device. It's called a Bobcat. It's got a shovel in front, and we see the back of it. And notice that I don't think I ever saw a Bobcat, certainly not in this position before, but it shows up quite well as something that's important to guide the vehicle. The other thing, it shows up at the other side of the road. So you don't have to see exactly the same thing to drive safely, in new situations. It learns to pay attention to things that are relevant. So here's another thing that's critical. We have a device or a program called a resimulator, and what that does is let us analyze how a learned network operates in new conditions, or we can also replay back old conditions. And what it does is it warps a real video adjusting for the current pose of the car, which is either the shift or the rotation. And it actually agrees quite well with what we see in the actual vehicle test. And we use that to predict the mean autonomous distance or MAD before we actually go out on the road. This is what the display looks like. And here you see what's highlighted, what's important. This is the noodle showing the preferred path. When this green thing is on, it means it's in autonomous mode. If the car drifts outside of what we feel is a safe margin, then it flags that as a failure. So let's see. This little video that we made here, I think it's self-explanatory. So we modify the position of the car. The original image. This is if you shift it left, you shift it right. So you get some artifacts, but they don't seem to be important. Here's it in action. It's the region of interest. And you'll see some cars come by. And you'll see that they're never actually highlighted in green, even though they're warped quite a bit. This car doesn't look very happy because it's not affecting where we're going to drive. This seems to be a pretty effective method for evaluating our system before we get on a public road. Okay. So another example then is after we've learned that the system works in the resimulator, we can also take it on to the closed courses that we have at the Bellworks facility. And here we're learning how to turn. So we have PilotNet. We have an additional input which is based on rough localization. And that says either go straight, take the next left turn, or take the next right turn. We don't say when to make the turn, but look at the surroundings and decide where to go. For these experiments, we have 3 cameras, one looking forward, one looking to the right, and one looking to the left. Let's see if this goes here. This is the parking lot. This is my test driver. His name is Luke. He wasn't paying a whole lot of attention. Only Luke is in the car now. We have an outside kill switch. So it's turning right. pace with keeping right, not making a hard turn, going straight. That's the drone pilot in the center there. This is just driving based on the cameras. There's no LiDAR, there's no map localization, nothing like that. It's a crude GPS telling it when to take the next turn. Okay, let's move on. Okay, now we're going on the main road. This is the 8-mile run for getting ice cream to fill the freezer in the office. Let's see, this should go. This is speeded up 3 or 4 times. And this is Chen Yi Chen, who's the safety driver. And we had a second safety person in the car, Artem Providin. We're driving, in the area of Monmouth County in New Jersey. So what Chen Yi did was to say, when you get within a certain distance of the intersection, either go straight, go left, or go right. So it requires having at least the crude GPS. But there's no final localization, there's no map. I think you get the idea. I'm not going to spend more time on it, but it's pretty clear that this works quite well. Okay. This is a video of work we did when we had early snow in December of last year. And this was a case where the car was trained on data only from California, about 10 hours of California data. It worked reasonably well. I wanted to show you what it looks like. It started snowing in the afternoon versus in the car. I went out with my cell phone, took a photo, got it onto the Bellworks lot. This is driving around the Bellworks private road first to get us some confidence that we're not going to do anything terrible. But you see, there's no lane marking. It's pretty messy. This is a dirt road in a nearby park. I never saw anything like this before in the training day. This is on local road, Middletown Road. Then Chen Yi took that at night. It's pretty amazing that this worked at all. Now this is the GoPro image, the actual, which is somewhat better. This is the image from the car. You can see what's being highlighted. He drove it back into the garage building. Then Saturday morning, Ursula and I went out. It was cold and clear and blowing hard, and a lot of reflections off the pavement. You see the snow blowing out of the trees. And so it's basically following now, I think, the ruts in the road, everything's snow covered. This wasn't perfect, but it was surprisingly good not having been trained on this kind of environment. One thing you notice here, look at the car in front. This is in Homedale Village. So we're staying in the lane better than the human driver when we're going back to the garage. Okay. This is done in March by Chen Yi using a network which was trained with some snow, 3 times speed up. This was just done about 3 weeks ago. So this is sort of where we are now. We've had an unusual amount of snow in March. Apparently it snowed yesterday. So the bottom view is from a chase car. That's the view from the driving camera in the top. And then you can see Chen Yi there with his hands on his lap on the left. The reason I'm showing along clip it. It's not edited. You just see, what's happening. It didn't just pick out the 10 seconds when it worked. And there's one more here. This is, I think, fairly remarkable that it works at all. I think you can conclude from this that perception it can be licked. I don't think that's insurmountable. Okay, so moving on, I just want to summarize. We had some time for discussion. We've made good progress in driving without prior guessing of task partitioning, but a lot more work needs to be done to get to required safety. And we think that by combining systems like this with other systems, we have a shot at getting there. One thing I want to mention is that there was a workshop at NIPS this last December, and I think it was the conclusion of numerous speakers. I wasn't one of them there, but many people felt that to really solve this problem, you can do level 5, drive anywhere, just like a human, is AI complete. And that's an open question. We just don't really know at this stage whether we can create a system that can drive safely anywhere, anytime. And we should probably get a pretty good idea what the answer is in the next 5 years or so. Thank you.